All right, let's look at number 7. I think that's where we are. Calculate the, can you see that? Calculate the 7a. Molar entropy of a constant volume sample of neon at 500 Kelvin. And they give you, given that it is 146.22 joule per k-mole at 298 Kelvin. Oh, that's different. How do we represent that? Well, we have neon, it says. So we have neon gas at 298 Kelvin. We know that its molar entropy is 146.22 joule per K. I'm pretty sure that it should be given joule per K mole, because it's a molar entropy. And let's look at that again. What is the process? What is the molar entropy of a constant volume sample at 500? So we know what it is at 298, and they're asking us what is it at 500. So how about we treat this as a constant volume change from one temperature to another, like a constant volume heating. Okay, that's what it is. So it occupies a volume. I don't know what it is. And delta V is 0. Constant volume heating. Another way of saying that, of course, is constant volume isochoric. Right. And of course I still have neon, but now instead of 298 I have 500 Kelvin, and let's call that V1. V2 equals V1, but I'm being asked to find the molar entropy. All right. There is no equation of state that includes S. PV-nRT, equation of state. There isn't a similar one that includes S. So it doesn't matter that I have a couple of variables. I can't rearrange them into a formula for S. But think about this. If I knew what delta S was, I actually could calculate that. See where this is going? Delta S is final minus initial. So if I know this, calculated independently, then this is equal to this guy minus this guy. Now this is my only unknown. So that's the route that we'll take. So when you're asked to find or determine the molar entropy of a substance under certain conditions, then look for a molar entropy that's given and for a delta S that you can determine, and then we'll put it together and isolate the unknown. So this, call this 1, and let's call this 2, state 1, state 2. And so of course what we have is the molar entropy in the first plus that delta S, and its molar, delta S molar. That will give me my molar entropy number 2, and that's what I'm looking for. So this is known. This is what I need to find. So I'm looking for delta S of a constant volume heating change. So where do I go? ds is equal to dq reversible over temperature. This time I don't have a constant pressure, but I have a constant volume. And so really that's dq sub v. And what is q sub v? Remember, q sub p is H, or enthalpy, and q sub v, you got it, internal energy. Okay, and you remember what du is, or delta u, but I'm inside the change at the moment. Du is n CV molar dt. So careful, don't put delta t. It would be delta t if that was delta u. It's du. And that's all over temperature. So then I'm going to integrate this. So I get delta S is equal to, what can I pull outside? Anything? N and CV molar. Integral 1 over T dt. And now you'll remember the formula. And unless you were asked to show the derivation, I don't think you would be. If you remember that it's N CV molar ln T final over T initial, then go for it and start with that formula. I just like starting with the same starting point each time and then working our way through, because the skills here are really important for this course. Now, one thing, do I know the heat capacity? I know it's neon, and so I would look that up. So this, I don't actually have a number of moles, and so my answer is going to be not in joule per Kelvin, but joule per K mole, because I won't be able to cancel that number of moles. So this, it's okay if you don't have that. It'll end up, your working equation then is just CV molar ln T final over T initial. It just means that your answer is going to be in the same units as CV molar, which is joule per K mole. And this is, when you look it up, you'll find, most likely you'll find a CP value, and remember that you just have to take a value of R, 8.3145 joule per K mole, away from it. So when we look up CP, we have 20.786 joule per K mole. I'm taking 8 away from that, and I'm left with 12.472 joule per K mole. And how about we continue writing here, ln of T final, T initial. The T final was 500, and the T initial is 298. Remember to get rid of those units. Okay, delta S then is equal to 500 on 298, 1.6778, and I'll take the ln of that and multiply it by 12.472. 6.45 joules per K mole. That's delta S, right. But if you look back up here, I'm trying to find the molar volume, or molar entropy in the second state. So that, I'll write a little therefore, Sm in the second state is equal to Sm in the first, plus delta S that we just found. And that is given 146.22 plus delta S 6.45. Now, just a quick look. See, I will put the units on the outside as joule per K mole. Just want to make sure that that was also joule per K mole and not something like a kilojoule. So just be careful when you do things like that. Oops. There we go. Monitor's turning off. There's not much movement in here. We're ready to add that. So that's still showing 6.45. We'll write it again. 146.22. I should be able to do that in my head, but not this time. Day 152.67. Do I keep all those? What's the rule? What's the rule? You look at the decimal places because it's addition, and I would have 2 decimal places plus another number with 2 decimal places. So my final answer should have 2 decimal places, and the part that comes before is required, so I end up getting 5 sig figs on this answer. So that's number 7. It's a good question. Really good question. Make sure you know how to do that.